And you have a whole lot smaller quantity of air here than you had water in Joule's experiment. So for both of those reasons, the heat capacity is probably something on the order of 10,000 times smaller. With a 10,000 times smaller heat capacity, do you think you measure a temperature difference with your two thermocouples there?
Probably, yeah.
Yes, you do. Thomson, in fact, measured a non-zero internal pressure. Using a much lower heat capacity, you can observe the temperature change. And with air, you in fact observe that there is a non-zero internal pressure. That turns out to be somewhat important, and in fact you see it right here. William Thomson, later Lord Kelvin, he was knighted for having made this discovery, and he took the name Kelvin when he was knighted. And it's the name Kelvin that we know today because of a certain temperature scale. So what we see is that for air anyway, the internal pressure is not equal to zero.
Yeah.
Zoom back out and put that back there so it sees the top of the paper instead of the bottom. So this turns out to be somewhat interesting and important. How do we go about evaluating it? This is where life gets sort of interesting.
Dr. Sal, since they didn't have all the modern equipment, how did they know how to evaluate their findings to know they were correct or not?
Replicate measurements.
The same way we do today.
Equation after
We
equation.
can't. When you discover something brand new, you have to trust your discovery, trust your laboratory work that discovered that. If it's brand new, there's no explanation, there's no theory for it. Joule recognized that the internal pressure had something to do with intermolecular forces, with ways molecules interact with each other. And he was asking the question, do molecules interact with each other? And Joule said no, on the basis of his experiment. Thomson recognized the flaw and said, yeah, they do interact with each other, but not very strongly, because it's only a minor effect. It doesn't change the internal energy much. But how do they know it was right? They have to trust their evidence. The same way we do today. We have to trust what we see. At some later stage, there may be a theory which explains it, which can help us better believe it, maybe. But do you believe theory? Or do you believe what you see in the experiments you do?
Always believe the data.
Well, your experiments have to fit your data, so it's always data first. Why do you think the world has spent billions and billions and billions of dollars building the CERN collider in that 15-kilometer ring underneath 3 countries?
Better data.
It's underground, and it covers the borders between Switzerland, France.
I think the third one's Germany?
I think the third one is Germany.
What is it called?
It's CERN, C-E-R-N, which is an acronym in French.
Center European Research Nuclear.
Something like that, yeah. It's a French acronym. They just spent 4 or 5 years ago something on the order of another $4 billion to upgrade that ring so it can make even collisions of protons at even larger energy. Why? Something called the Standard Model, which describes the inner workings of atoms and molecules from a physics perspective. What is an electron? What is a proton? What do those quarks inside do like, and so forth? The the standard model that describes nuclear and subnuclear physics. Well, the standard model suggests that there are a series of other particles that haven't been discovered yet.
The quarks are even more than
Well, quarks were some of them. When the standard model was first developed, and it's been refined quite a bit since then in the 1960s or 70s, it predicted all kinds of things that hadn't been discovered. And physicists worldwide had been trying to discover them. Quarks were among those, the quarks and the anti-quarks both. But there was one particle left that hadn't been discovered yet. It's called the Higgs boson, that was predicted by someone Higgs. CERN spent all that money to upgrade their range to get even more powerful collisions to try and search for the Higgs boson. They apparently found it, although there is some dispute in the community of whether they truly found it or they see an artifact in their data. They found it at the highest energy the rain could produce, and they found 2 Higgs bosons. And on that basis, they published a paper and said, we found it, and Nobel Prizes were awarded and so forth. But there's still some disagreement in the community of whether they saw something that was real or saw an artifact in the data, and we are dealing with an experiment that is that complex. Whether it's an artifact in the data is a very, very thorny question. That's why they did that, to try and prove that model. Well, models in chemistry don't require that kind of engineering to prove or disprove. But in essence, what we have that we think is theory that proves something are models. The perfect gas law is a model of gas behavior. And it works reasonably well, but we've seen that for real gases, it's not precisely correct.